Good afternoon all. I welcome you back to our lecture series. Hope you all enjoyed your lunch. We are now starting with the special inorganic lecture by Professor Ramaswamy Murugavel. I would like to request Professor R. Ragarajan to please introduce and invite the guest speaker.
Thank you. I must first of all offer my very sincere thanks to Professor Murugavel. Within a short notice, he accepted our invitation, and his name was quite unanimous in the section. And that's why when Professor Prasad asked me to do that, we did not waste any second or a minute, because all of us, we knew that he is going to be the speaker, but the most important thing is to convince him to come here within the short notice, which he has kindly agreed. And therefore, my sincere thanks to Professor Murugavel. He is an extremely busy personality, and he has a lot of commitments and other things. And as told by him, the short CV, which I would like to tell you, that he is currently a J.C. Bose National Fellow and the Biswas Balleput Distinguished Chair Professor at the Department of Chemistry, IIT Bombay. He also additionally holds the position of Professor in Charge, Institution of Eminence Project at IIT Bombay. He received his BSc and MSc degrees from the University of Madras and PhD from Indian Institute of Science, Bangalore in the year 1993. He carried out postdoctoral work at the University of Göttingen 1994-97 and joined as a chemistry faculty of IIT Bombay in December 1997. He is a fellow of the Indian Academy of Sciences, the Indian National Science Academy, and the Royal Society of Chemistry. He has been conferred with the J.C. Bose National Fellowship, Swarna Jayanti Fellowship, Alexander Wumholdt Fellowship, DAE SRC Outstanding Investigator Award, DFG Mercator Professorship, C.N.R. Rao National Prize in Chemical Sciences, S.C. Bhattacharya Award for Excellence in Research in Basic Sciences, DAE Young Scientist Award, CRSA Bronze Medal, MRSA Medal, and J.C. Ghosh Medal. His research work has been published in the form of more than 200 publications. Current research in Murugavel's lab includes metal phosphate framework structures, covalent organic frameworks, phosphate-based molecular magnets, and single-source precursor chemistry for metal phosphates and phosphites. With this very small introduction, I would request my friend, Professor Murugavel, to give a talk.
I'm sorry. Okay, I'm sorry. Okay. Okay, so the phosphorus combines with the oxygen and makes several kinds of anions actually. Okay, of orthophosphate, pyrophosphate, metaphosphate, and the number of phosphates. Okay, so the combination of phosphorus and oxygen gives you a large number of anions, which can combine with one or more cations and produce a large amount of metal phosphates. I'm not going to go through each and every example which is shown here. Just to give you a kind of a table, you would appreciate. I think you can make phosphate containing molecules where the phosphorus is either orthophosphate or pyrophosphate, or even dihydrogen phosphates like the one what is shown here. And they have been mainly useful in energy-related areas in the last 10 to 15 years, and more so since Goodenough's work of lithium cobalt phosphate being an essential constituent of lithium-ion batteries. Okay, this is kind of just trying to justify, I think, why our group has been kind of working for such a long time on phosphates. Okay, so people like Nagarajan would know that I think you combine phosphoric acid with the metal ions under various conditions, they form metal phosphates. Okay, so you take phosphoric acid and put some metal ion, metal sulfate, metal chloride, you will get a metal phosphates. When performed in the presence of a template or an amine, you can actually convert these condensed metal phosphate materials into framework materials, what Professor Rao and Professor Nagarajan in IISc Bangalore pioneered about 20 years ago. Okay, how do you convert this so-called condensed matter into something more porous and do some applications? One downside of such an approach is that it often requires high temperature, and if not high pressure, at least autogeneous pressure. Okay, essentially you do perform all these reactions in an autoclave, so actually you don't have much control on what is going on until you open the lid of the reactor and find out what is there inside. Okay. So as a result of this application of higher temperatures and higher pressures, you often end up in problems associated with the phase purity. Okay? Normally you get multiple phases, and sometimes even metal oxides, depending on under what conditions you really perform. Okay? Some of these problems have been kind of highlighted in a review which I wrote quite long ago. Okay? When we actually are transitioning from framework phosphates to molecular phosphates. Today's lecture I'm just going to kind of narrate 4 short stories which essentially involves organic modification of phosphoric acid. As you know, phosphoric acid has been around for a long time around with us. Okay? It's a really old molecule. The moment you start compromising one or more of these acidic hydrogens, as you know, it's a tribasic acid. So, I mean, they have taught us in the second year BSc, I think, maybe in the first year BSc, how we have a pKa1, pKa2, pKa3, they are very different. How we can go from H3PO4 to H2PO4 minus to HPO42 minus to PO43 minus. I think you remember these graphs, So, that's what exactly I think we try to kind of exploit. The first molecule what I show here is essentially 2 of these acidic protons have been compromised by 2 T-butyl groups, tertiary groups, which not only impart solubility in organic solvents, but also makes this molecule highly thermally reliable. I'll come to that in a minute. Without compromising on the solubility, you can actually knock off only one of the acidic protons and not 2 in the form of a 2,6-diisopropyl phenyl derivative. Okay? So essentially you have 2 T-butyl groups here. Here also you still have 2 alkyl groups in the form of 2 substituents on the phenyl ring. So solubility is not compromised, but the bonus here is that you have an extra acidic proton. So essentially this will form a POO minus monoanion, whereas this will form a PO3 2 minus dianion. And you can actually do an isomorphic replacement of the OH with the NHR or NH2. These are called as phosphonamides, which I may or may not touch upon today, depending on the kind of time that I would have at my disposal. Okay. But however, I will definitely switch over to this particular area where I replace this bulky aryl group by an alkyl group. These molecules are thermally very unstable. They are transient. You can't make them and keep it in the desktop. You need to kind of make and use them extremely unstable molecules, but they can be actually exploited for some battery and supercapacitor applications, which I will touch upon towards the end of the lecture. Okay, let me just begin with this, this famous molecule, which was published in an obscure journal, I think long ago by some, Polish chemist. I think it's I don't know which journal it was. I think. This particular molecule, as I said, has got two tubular groups on phosphoric acid. This is actually soluble from water to pentane. It's soluble in pentane because of the two butyl groups. It's soluble in water because it's still a phosphorus acid, POH. Okay? So essentially, every solvent you have in your cupboard can be used for performing the reactions with this. The second bonus in using this material is that you can use this POH to form a metal phosphate, and then slowly ask this tubular group to just leave the molecule by simple beta hydride elimination. Okay? I think all organic chemists know about T-butoxy group. T-butoxy group, I think, will bite back through the beta hydrogen and form. So essentially, you can. Oh God, what is that too close? Essentially, I call this as an organic soluble form of phosphoric acid. This is phosphoric acid. This is the dibutyl ester. So the moment you make this compound, I think my first student Satyendran, I think, worked on this for his PhD. You make this and keep it on the table and go for lunch and come back. It will be this. It is so very unstable. It will undergo at room temperature, either hydrolysis or thermal elimination to give rise this. The advantage is that you can take this molecule and react with it. I mean, I'm not going to really elaborate each of these reactions. You can make a large number of metal clusters and polymers and cages. So, for example, this is a zero-dimensional cage. I may touch upon one of the examples of a polymer, or you can form a 2D networks. But good thing about all these molecules is that the only organic content is the tubular group. Everything else is inorganic. So, as a result, if you start heating this, all these molecules which are shown in the left and left top part of the transparency to about 150 to 200 degrees centigrade, they will lose tubular group as isobutene and produce the corresponding, hydrogen phosphates, which go on to self-condense to form, either pyrophosphates or metaphosphates, depending on what is the composition to start with. Yeah, I'll just show one example, a very early example from my group, is the cadmium phosphate polymer, which is a one-dimensional polymer. As you can see, the whole backbone is inorganic. The only organic part is the R group sitting on the top, that is the tubular group. So the coordinated water leaves at a fairly low temperature, about 70 degrees, 80 degrees centigrade. And you see this kind of temperature, weight loss, which is parallel to the y-axis almost, which amounts to about 50% of the weight, which is the loss of tubular group as a butene, then produces POH on the surface, which goes on to self-condense and make this. So what is important to note here is that the formation of metal phosphate material in the nanocrystalline form happens at temperatures as low as 300 degrees centigrade, and there is no impurity of any kind, because nothing else, because this is a single crystalline polymer, so you have 100% pure compound in your flask. All that you are doing is the thermal elimination of the butyl group. So as a result, you have nothing else other than this. Okay, it's 100% only one product, no carbon impurity, no metal hydroxides, no metal oxides, and so on and so forth. So of course, cadmium is boring. I mean, what do you do with the cadmium phosphate? But what is more interesting, I think you can follow this by in situ PXRD. I think this is how in situ PXRDs look like 20 years back, but today they look much better than this. Or you can do a ex situ IR spectroscopy. You can follow these transformations. As you can see, at 350, you get this nanocrystalline cadmium phosphate, which goes on to crystallize at 500 degrees centigrade as single crystals, still in the nano regime, or maybe a few tons of nanometers of cadmium phosphate. So what we did is in 2002, we took it up about really 2 decades later. Only thing is we changed the metal from now cadmium to cobalt, because by then I think Nosara has published his famous papers on cobalt phosphates, which would split water, produce hydrogen and oxygen. So we knew that I think it's only time before we actually put this molecule into some use. So it's a very simple reaction. The molecule is pretty much similar to what I showed in the previous slide. Okay, this one, pretty much similar. Only thing is the cobalt, the cadmium has been replaced by cobalt. So now what you have is this polymer. You can do a single crystal structure. This is what backbone looks like. So a pair of cobalt is bridged by triply bridged by the DTP groups, with these dimeric units are bridged by another DTPP. So essentially it's the ML2 polymer. So as a result, what happens is that there's no water like in the previous case. As you can see, at as low as 100 degrees centigrade, you lose all the organic content in one go in the form of isobutene and produce at 150, 160 degrees centigrade a cobalt phosphate, which is a cobalt H2PO4 2 times. Okay, so then what happens in this region is that H2PO4 being metastable, under those conditions, they actually cross-link and form COPO3 twice. Okay, what you have at 300 is this PO3 twice. And of course, in fact, it was published in somewhere, 2007, 2008 in inorganic chemistry. But this is when Subbu arrived just 2017 or 2018 to my department. I think materials chemist or electrochemist, I would say. So he was actually working on this nano carbon fluorides, which are essentially actually made from, those of you who know Vivek Polshetty was work in TFR, who makes this nano silica. So essentially take this nano silica and deposit carbon and alkali wash your silica, and then you get this porous carbon. Essentially it's a complementary dye. Okay, so in this now we essentially do this reaction, this cobalt phosphate formation. Instead of doing it in the flask, we did this inside this carbon nanostructure. So essentially, this is your pure carbon. This is the carbon with cobalt phosphate. And actually, I mean, like I'm just presenting in not the same order as we got the results, because we just were following the TGA as the guiding principle that we decompose the compound at 150 degrees centigrade, and then at 200 and 250. Essentially, we just kind of looking at the catalytic behavior of this material decomposed at different temperatures for different reasons. Because sorry for this non-standard abbreviation, DP stands for dihydrogen phosphate, which is H2PO4, and MP stands for metaphosphate, which is PO3. Okay. So what happens is that when you start, actually this is where I think my iPad will help me, just to correct this. This H2. So essentially, you have predominantly H2PO4 phase at 150. If you had followed this TGA, at this point of time, the dihydrogen phosphate is converting into metaphosphate. So what you have at 200 centigrade is a mixture of both dihydrogen phosphate and metaphosphate. And now you hit to 250, by the time you have completely exhausted all the POH groups, and what you have is only the metaphosphate. So essentially, dihydrogen phosphate one extreme, and metaphosphate other extreme, and something in between. As luck would have it, or I mean, whatever you call it as, the best catalyst turns out to be the one which is the mixture of dihydrogen phosphate and metaphosphate. Don Tilley, a friend of mine at Berkeley, has worked on this cobalt phosphates, metaphosphate, and written a number of advanced functional material papers towards 2015, 2016, and has batted for cobalt metaphosphate as being the most productive form of cobalt phosphate, which would split water into hydrogen and oxygen. Okay. And this will be an antithesis to his work, although we know each other very well. And what is important is that my collaboration with Subbu, who is actually also a Raman expert, so he would go on to do a Raman imaging. So this would be the Raman spectrum of the pure dihydrogen phosphate, the DP phase, and this will be the Raman spectrum of the metaphosphate phase. So when you do actually a Raman mapping or Raman imaging, whatever you call it as, you can see that predominantly green at 150 and predominantly red at 250, and what at 150 is at 200 is that regions of green and red merged together. Okay, so and as you can see, this is the concentration plot. I think this is predominantly dihydrogen, predominantly meta. This is a mixture of these three phases. Okay. Now, I'm not just going to spend too much time on this. Actually, I mean, like a complete characterization, whatever needs to be done. I think we have characterized the material that is formed by, whatever technique one should actually put them through. Most importantly, the XPS. And let me just not, spend time on, explaining each one of these. So essentially, the material is what we have seen from other spectroscopy techniques. So this is a linear sweep in a voltavogram. What you see in the left top, it turns out that I think the one which is mixture of dihydrogen phosphate and metaphosphate, the red line has the lowest onset potential or the lowest over potential for water becoming oxygen. So the other two being, this was kind of initially was a surprise. I think if we didn't go for Raman mapping initially, something was not adding up. The 150 is having a higher over potential, so is 250, but why is 200 is showing lower potential? So we went back and looked at the Raman mapping and figured out. I think this paper actually got accepted within 3 days of submission in small, with some wonderful comments, because some of the because Daniel Nosora started this, I think, about 10 to 12 years ago, and a lot of people are actually trying to figure out which phosphate, the meta, pyro, ortho, or dihydrogen phosphate, which is most active form. So it turns out that I think you need to have a bronzed acidity as well as the metaphosphate for promotion of cobalt 2 to cobalt 3, which is a very important stage. Okay, so at the point of time when we published this, I think pretty much it remains still the same. So this is Don Chile's work where he is shown at 600 millivolts. I'm sorry, the onset potential for nano COP3 twice. So this 301, I think, probably is the at that point of time a record for cobalt phosphate material, which is the dihydrogen phosphate metaphosphate. Okay, so I think as you can see, I think this is the most famous work of Daniel Nosora, which was about 100 millivolts, still higher than that of what we would report, because we are 10 years anyway behind. That doesn't really matter. Okay, so I'm just going to leave it that at this point. I think there are lots of work we are doing with other forms of cobalt phosphate. That would be for another day for a full lecture, but since I wanted to give an overview, I will just switch gears. I think probably I would skip this. This is, I think, a piece of work that I'm working with a chemical engineer who works on cements for dental filling and bone reinforcement. This is essentially now, see, from cadmium to cobalt to calcium. Okay, so the ligand remains the same and the roles change. Okay, so now calcium, we made this polymer pretty much same structure, calcium being a much larger cation. So it picks up 2 water molecules, it's still a polymer. So I think I just kind of skip all these details only to show you that this one polymer, I can make so many different ceramic phases at different conditions. I can either do this in a bulk thermolysis route, or I can do, I'm sorry, this is too close to each other, the back and the forward. Okay, so I can do a bulk thermolysis, or I can do an hydrothermal thermolysis without an added reagent or with an added reagent. So I can make an hydroxyapatite, I think somewhere here. Where is that? Here. Okay, hydroxyapatite. I can make all these phases. I think the second paper in the series has just appeared a few weeks ago, or probably this week, I would say. I think, and there's a lot of work which we are doing with bone filling with this the beauty about this molecule is that this is organic soluble. I can dissolve this in acetonitrile, methanol, THF, and I can actually take in an organic medium or even methanol water mixture, and then decompose it and then get whatever form you want. Some pH playing around. I think we do this normally in organic medium. Jayesh Bellare, who is my colleague in chemical engineering, he is kind of trying to do this in aqueous medium, and he is trying to find ways of osteoporosis, bone filling technology. I think it's something we have to wait and see whether it really works. But it's an organic soluble calcium phosphate, which may have some application. Okay, so this actually is nanocrystals of hydroxyapatite, which has been made by this method. Okay, these are only being used as the bone fillers. Okay, so let me just shift the gears and go to the story 2. Now I'm going to just kind of ask for an extra bronzed proton, because I had compromised earlier 2 hydrogens. Now I only compromised 1 hydrogen. I still have a 2,6-diisopropyl, and this will form a bulk of my research between 2010, I would say 2008 to 2018, where we have shown, I think this is a completely different topic, where you used this particular building block. Essentially, it's like a PO3 2 minus. Okay, I think maybe I just take a minute to tell you that. In 1981, a major discovery came out of Edith Flanagan. Where is she from? She's from Alpos. She's from not DuPont. What was there in Bhopal which led to the gas tragedy? What company is it? No, what is the company's name? Union Carbide, yeah. So Union Carbide introduced the first zeolite. Okay, Union Carbide introduced the first zeolite in the 50s. And in 1981, Edith Flanagan, a remarkable lady, I think she did some major discoveries. One is the silica light in 1978, the very famous, the porous silica. She would follow up that research with a classical paper in JSCS 1981 published. I think it's been gone on to be cited some 40,000 times as of now, where she has shown that I can take a Al3 plus cation and they get a PO4 3 cation and form a alpha. Okay, this is it. And then the people put chromium, the people put a manganese, iron, and made lots of modifications and used for catalysis. Okay, alpos actually revolutionized, the porous solids, because until the time the porous solids mean silicates. So essentially silicates are SiO2, and you replace some of the silicons with some hetero metals like titanium. The famous, work of, Paul Rathaswamy and others in Pune in the 80s. These are, 2 plus cations and 4 plus cations, 4 minus anions, to 3 plus cations and 3 minus anions. So unfortunately for Flanagan, there are not many elements in the periodic table which show stable 3 plus cationic state. Actually, aluminum is the only one for that matter, which forms regular octahedra and still 3 plus. The one more element which actually probably would show octahedral geometry is gallium, which is very expensive. The other 3 plus cations are in the lanthanide series. Coordination numbers are 9, 10, 11. They don't form regular structures. Okay. So essentially, whatever she could do was only around one element, namely Al3 plus, because PO4 is 3 minus. Because the whole idea is to make an hydrophobic, not hydrophilic, but hydrophobic, porous material. So the modification what we did around 2005, I think Kupu's work with this, is that you have a PO3 2 minus instead of a PO4 3 minus. Instead of bringing an Al3 plus and forming a PO4 3 minus, now I'm bringing a PO3 2 minus, and I open the entire first order transition metal series, zinc, cobalt, manganese, nickel. I can make now a porous solid with every element in the first order transition metals, because the divalent metal ions are plenty, whereas trivalent metal ions, which form regular octahedral geometries, are very, very small in number. In fact, aluminum is the only cheap metal. So Flanagan's research is very important, but was restrictive in the sense that you cannot really go beyond aluminum, and you could only substitute Fe3 plus, Cr3 plus, and small amounts. If you substitute more, then there's a phase separation and other kinds of problems. Okay, that's a kind of totally unrelated information, but I just thought for the students it will be of some use. So what we did was that the moment you have a UO4 N minus, you can form this so-called, you can take this tetrahedras and form single rings, and put single rings over single rings and form a double ring, or single rings in another fashion and form a double 6 rings, or single and double you mix together and form a soda light, and take any of these 2 building blocks and stick together with a proper chemical glue and make zeolites. I think this is kind of pretty much, I think, Singh is here, and Singh, I think the way they do retrosynthetic analysis, right? They take a natural product and then they break into smaller rings and then make it. So zeolite is essentially, you can take a knife and cut this and say there is nothing but a PO4 3 minus or, Al3 plus. I think that's what we just tried to do this. Now the job as a synthetic main group chemist is, can we walk along from left to right rather than from right to left? So can we start from a molecule which is having a UO4N minus and build a single ring and a double ring and so on and so forth. At each stage, isolate the product, characterize it and say that this is what I have. I made G1, G2, generation 1, generation 2, generation 3, and finally I have a zeolite. I think that's, it's more like fun we started with in the beginning. So this is what I just talked about. I think phosphoric acid, one hydrogen is replaced by a R group. So this is insoluble in organic solvents. When say insoluble is in organic solvents, I have, lyophilized by putting this in a 2,6 isopropyl group. As one would expect, this molecule goes on to react with the divalent metal ion, namely zinc 2 plus. The reason why I use zinc 2 plus because it's a divalent metal ion which is diamagnetic, so I can do NMR of these samples very easily and know what's going on. I don't have to depend only on single crystal structures. So we could immediately form this double 4 ring, which I showed in the previous page cartoon as one of the fundamental building blocks most often encountered in the fundamental building blocks of zeolites. Okay, now this is what we have here. We made this compound. So essentially it's a cutout of a zeolite. Other than that, the 8 corners have been capped by organic terminators. Here is a 2,6 isopropyl phenoxide, and here L is nothing but a methanol which is used as a solvent. zinc is essentially the tri-coordinate. The fourth coordination has just been kind of compensated by a loosely hanging around methanol, which can be kicked out by bringing in a stronger Lewis base such as choline, because choline is 2,4,6-trimethylpyridine. So that would replace methanol and form a compound which is a fine microporous powder, microcrystalline powder, would now grow as a single crystals, so that we can convince ourselves and others that we do have a double 4 ring in the flask, and which is also soluble. Then you can do a solution number and say that. So see this, I have taken a knife and cut out my zeolite, taken a small piece like cutting a birthday cake. So this is your piece, this is your building block. Now you do whatever you want with this. So what you do with this is the next few slides. Okay, as I said, I think zinc is what we started with. Then I think we realized that I think there are multiple uses if you have a paramagnetic metal for magnetic MOFs and things like that. So we put cobalt, we put copper, we put manganese, and we could make all of these double 4 rings. To cut a long story short, I think we could only use hydrogen bonds as the linkers. Is probably the first and only examples to date are purely hydrogen bonded metal phosphate zeolitic materials, where we, instead of using collodion, which I showed in the previous slide, I still use pyridines, but the pyridines are decorated with a additional functional group. It could be an hydroxypyridine or aminopyridine, or it could be a pyridine methanol, pyridine ethanol, or it could be even a pyrazole. Today morning I learned a lot about pyrazoles. I may be writing to K and Singh because I need some pyrazoles from him. Okay, there are some nice pyrazoles. So you can use these and form periodic structures. It's a railroad and honeycomb, and you can have a three-dimensional structures. Here, these building blocks are only held by multiple hydrogen bonds. Again, just to cut a long story short, you have equal number of intercubane and intracubane hydrogen bonds, more intercubane hydrogen bonds, and only intercubane hydrogen bonds. So 2 to 1 to 3 and 0 to 4 is the number of inter to intracubane hydrogen bonds. You can play around with the number of hydrogen bonds and build this. And of course, these are good to publish a nice paper and go on to, but I think practically, I think these will fall off at 300, 350 centigrade. You need covalently linked ones. Again, I just kind of rush up. I think, Raja, how much do you time? 20 minutes? 20 minutes. Okay, so then we would that's when I think Yagi is kind of publishing a lot of papers using this kind of spaces like a 4,4 by pyridine. So we kind of borrowed a part of MOF chemistry, but this is not MOF chemistry. MOF chemistry is all about metal complexes. But here you have a main group phosphate, okay, and then you have a linker. So it's kind of an hybridized structure. You have an inorganic phosphate, building block, and then you bring in an organic spacer and build this together. So depending on the cubane to cubane to cubane angle, which is acute or obtuse, you can form either a diamondoid structure such as what you're shown here, or even you can form something like Kagome type of lattice. So you have essentially 3 cubanes forming a micropore, and 6 such edifices forming a mesopore or a macropore. This is about 24, 25 angstroms, and this is about 7 angstroms. So essentially you have a mesopore and a micropore within the structure. Okay. We have used for from catalysis and other things. Probably I think I would probably kind of leave it for some other day. So if you're actually seeing this carefully, actually my phosphorus is kind of blocked. I have this wanted at one point of time to build the molecule. So once I build the molecule, it's really a disturbance rather than an asset actually. I think you want to get rid of this at some point of time. So we cannot really get rid of it. You can try to hydrolyze this, the whole structure collapses to some intractable material. So all that you have to do is you have to work with the methanol or a DMSO, okay? And then that's when I think Kamna came along, and then she did some very interesting modification. I think she had some organic chemistry background from Jaipur. I think she kind of said, I think we'll put a functional group in the para position. It's essentially the same molecule which I've been using for 7-8 years. So she nitrated the phenol and then reduced it with the amino. And then essentially the same structure what I published about 2007, 2008. But the only thing is now I have 4 amino decorations. So the amino immediately throws up 2 possibilities. One is that I can use a dialdehyde and form a COF. I think most of you know what is a COF is. And second thing is that I also make my cubane highly basic in the surface. I'll show in the next slide. Now if I take this cubane which is decorated with an amino group rather than with the hydrogen, I essentially have these 4 NH2 groups which is in the corner of the cavity. So essentially I get a structure where the channels is no longer are hydrophobic, they become hydrophilic and basic. Okay, so the first, ever example we could demonstrate was, carbon monoxide and carbon dioxide, adsorption to this. Okay, so essentially you have a channel which has been decorated with the NH2 groups. So she would go actually one step ahead. This is, I think, it's a beautiful modification. It will look stupid for an organic chemist. Just acetylate this amino group and form an acetyl group. Now this molecule is Janus type. Okay, I think all of you understand what is an Janus. I think double-faced. This is a PO3S2 whose job is to build a cluster. And here I have just a acetyl group. The CO function is that to perform what methanol was doing before. So essentially, this forms a cubane, and the C double bond O bites a neighbor. So essentially, we wanted to use all the 8 corners of the cubane to build a zeolite, and we could do this many, many years later. Since our first molecule 2006, 13 years later, we could show that just not by doing any complicated inorganic chemistry, by doing some simple organic chemistry at the para position of the phenyl ring, by putting a acetyl group. So essentially, this cubane, if you look at it, there are 4 COs biting this, and 4 from here is biting the other ones. So the structure is beautiful. Actually, this is one cubane connected to 8 more cubanes, and this is how the structure looks like. Okay, and if you in that molecule you have NH2, this molecule has NH. Still, this is again. Unfortunately, this is a bit more crowded because of the acetyl group, the COCH3. However, I think it's still porous. I think still these applications of this chemistry is still to be explored. Okay. This is the last strategy to build porous solids from the same strategy. This is something which we realized that we can even put a pyridine aldehyde instead of using an amino phosphate, and you can decorate your cubanes with the 4 formyl groups, and then simply take these and react with the, this is 4 formyl groups and react with the diamine. This could be as simple as the 1,4-diaminobenzene, or could be benzidines, or could be even extended benzidines. I think the number of examples we just showcased. Some of them are commercial, some of them are homegrown. So we can use this and form this, what we call as the morph-like coughs, or cough-like morphs, because they are morphs because they got metal, they are coughs because it's an amino aldehyde condensation to produce this highly functional surface. So essentially, if you look at this particular pore is having as many as, how many, 6 into 12 imine linkages. So essentially, you can actually grow palladium nanoparticles and cobalt nanoparticles and rhodium nanoparticles, which you have grown in the recent times, and do a lot of catalysis. Okay, I'll just skip this. And finally, I think, I'm not just finished the lecture, but finally to wind up at this part, this is something I think, every time we wrote a paper in this area, I think there's one question, one of the 3 referees would always ask is that, how are the structures being formed? Are there 4 of these anions and 4 of these cations are swimming around in solution? They just accidentally meet each other and form the cubane, or there's an hierarchy. There is an hierarchy means, I think you form a single ring first, and then goes to double ring, and double ring becomes, a zeolite. Okay, so 3 or 4 PhDs, about 10 or 15, years of work, I think solve this problem to some extent. I would say about 80 to 85%. I'd only just show you. I think this is the drawing board, structure. So this was a key molecule. Why are we getting double 4 ring? Why can't we get a single ring? So it took some time, but we could make a single ring. This is half of the double 4 ring. We could make, I'm sorry, half of this molecule. Once you make this molecule, you have a P double bond O and P double bond O hanging in the front and the back. So there are only 3 possibilities. I think this is not an organic molecule. I think one thing is, I have to tell you in my general lecture, this is my Phosphoric row, and this is just a cartoon. Okay? So he thought that suddenly my inorganic molecule turned into organic molecule. That's the problem of the that 2 groups out, but I think this is my problem of the PO to the nuclear. So this is one of the people who are bites. So when I have this application phase, polymer. This bite the next time, this bite the next time, and then take a side and form a polymer polymer. And why should come face to face? It will probably educate us to the land and initiate state of the land. If that is constant part, that will be a successful, likely 60% occurrence, statistical occurrence, namely primary polymer, zigzag polymer. And this is what we talk about in the field. This type of form, this is exactly the one which is becoming ironically carbon. Suppose my, this particular land sector, I can stop the data my hand, all over the pollination happens. One of the side reactions is using water with the polymer is the heat formation and transfer rates, right? All the polymer is water. So it's a polymer formation. Can we actually kind of, instead of this going from there, bend around, this way by this way, and this way by this way. I don't know, it's a double 4, I have a double 16. I want to go into something from a double 18, and if you want a double 10, double 20. Essentially, we set out the journey to, first of this is the greatest box that we have in the baby. So many students who go looking for the companies, actually, an applicant will go right from the right to it's always relevant to actually activate the system of the government and first we can sample the system of that molecule under the layer between box or physics and the it's kind of help us kind of all the people it's kind of one unified scheme how these various building blocks are formed. What nature has done is doing the feedback along the quantitative local are plain micro essentially single units are small structures form single units go strengths and specify one platform what are the what about what is the water that is actually the astronomical structure. So these are separate single things. If you allow to grow in this way, there is a polymer, you can pull it around and it's fine. When you give an example, colleague of mine has given me some alarm molecules don't exist in the place of the air. To be used for templates for decan or a decorar, and the carbon is not a different concept. These are typically take any money on the web so that this is the template, you put it inside and get everything. This is the last thing. And you can do an annex in this, on a column. That's before when you want to do the result. That is the field now. He actually shows that. I think the going back to the 1970s series, after I'm doing it, they showed me the process, but without doing the process. So what we have here is how to get the activity. Take a key book. Key book is even more unstable. Suppose somewhat they want to use these are more secure, the moment is problem. So we should make the company, we're not really talking more only on certain processes. Not with the specific development. We need to make it from a problem to be like the shop and managing from the develops. Express the big allocating the acid and then we will take it. So the same relation in order to the array use the double two. Array qualified but in the non-case from physics I had relative materiality. What was area activity before the molecule or because of now whereas the van der Waals interaction between the two. So as a result, you don't need a phosphate like the Manchester, you can make n minus 1 and equal to distance, and so we are around the so only ask for the help for relation to the we get a one or the other. As research, it looks at the people education area, because of the like I think I need to because of what that's good. One of the this method I normally get PDF or this method I use the test this is our model. This is how to work with anyway, I think conclude about phosphoric acid is very raw. Essentially, phosphoric acid old molecule. Just go to your organisms to go to the lab and then think about the essays, after the nuts, and then remove solvents, rare materials, phosphate, which for what to do in that. Okay, let's stop here. I can take questions.
Professor, Professor Murugavel, I think there is a good tea arranged by head of the department. You can certainly no issue. I mean, the tea is getting colder. Yeah, that's correct. So I will request our head of the department. I will request our head of the department to felicitate Professor Murugavel for kindly accepting and coming and giving a wonderful lecture. Thank you. Professor Ashok Prasad, can I announce that there is a tea outside? Or